All right, so we've been talking about describing vapor-liquid equilibrium, and we've been thinking about where equilibrium is in terms of our criteria for establishing equilibrium. And in doing that, we've arrived at the equation that's on the screen, which we've said is essentially the most general place we could start in terms of thinking about answering this question of the equilibrium criterion as it pertains to this idea of the fugacity of each component being equal in each phase that is in equilibrium with itself. And so we've talked a little bit about this particular equation, right, in terms of our equilibrium criterion, right? This left-hand side is the fugacity in the vapor phase, and the right-hand side here is our fugacity in the liquid phase. And so if we couple this up with the fact that the temperature in the vapor is going to be equal to the temperature in the liquid, and the pressure in the vapor is going to be equal to the pressure in the liquid, then we have our equilibrium criteria that we've talked about before. All right, and we said that this expression, this expansion for the fugacities of the vapor and the liquid phase that we have here on the screen is going to work well for us in situations so long as we aren't above the critical point. Basically, so long as there's a numerical value of the saturation vapor pressure for the particular component we're interested in at the system temperature that we're operating on. So that's one of the limitations that comes up in this most general result. But we don't need any assumptions to get here. We just need to have values to actually plug in. And so we're never going to go wrong by starting at this particular place. Now, the first part of the course, we're going to drill down to ideal VLE. We've talked a little bit about the ideal gas and the ideal solution ideas so far. And we've talked about the fact that Raoult's law is used to describe equilibrium, or this equality of fugacities of a component across the phases that are in equilibrium with one another in situations where the vapor is an ideal gas and the liquid phase is an ideal solution. And so we need to be comfortable with what both of those things mean and be comfortable with identifying circumstances where the ideal gas and ideal solution assumptions would be reasonable. But so if we have a situation where we have an ideal gas and an ideal solution, then things simplify down to Raoult's law, right? And so we've talked a little bit about this before, right? Saying that in the vapor phase, the ideal gas assumption allows us to say that the fugacity coefficient goes to 1. The ideal solution assumption allows us to say that the activity coefficient goes to 1 because we don't have any non-ideality in the liquid phase. This phi I sat term, right, we need to think about where this comes from. And if you go back to the other discussion of how we got to this expression, you'll see that this phi I sat term is simply the fugacity of component I at the saturated vapor pressure in the vapor phase, ultimately divided by the saturation vapor pressure. And so in that situation, if we're assuming that we have an ideal gas, that means that we're going to have this fugacity coefficient at the saturation condition go to unity as well. Now, we could say there that we need to make sure that the ideal gas assumption extends to the saturation vapor pressure of the mixture of the component at the system temperature, and that would be something we would need to check there in terms of justifying that last assumption. But if over the ranges that we're thinking at for the temperatures we're looking at, everything's ideal, then that goes to unity as well. We also talked a little bit about the Poynting factor. That's our last exponential term here that we're going to talk about right now. And we said that the Poynting factor is often equal to 1. It's often neglected in systems of most practical interest to us. One of the ways I like to think about this is to just do a little bit of an order of magnitude or a little bit of numerical analysis here to try to convince yourself that that's reasonable. So, if you take this ratio and you plug in values for water, so we could say 18 cubic centimeters per mole for water, and divide that by 83.14 cubic centimeters bar per mole Kelvin, and let's say we use 298 Kelvin as our temperature. Right, if you take a look at this, 83.14 times 298 is a pretty big number. So RT is a pretty big number in most cases compared to the volume term that we're getting here, is molar volume of the liquid that we're dealing with. And so as a result, the argument inside the integral here is often a pretty small number, right? We could calculate this out and see it's a small number in this case. And so long as the range of integration, or the difference between pi sat and p, is relatively small, and you're integrating a relatively small number that is in this integral, then you have a situation where the argument of the exponential is relatively small, and therefore the exponential of a relatively small number is pretty close to 1. And so oftentimes we see that the Poynting factor is essentially negligible, and can be taken as close to unity in these situations where we're at relatively moderate pressures and have this situation where the molar volumes are just relatively small, and RT is a relatively big number compared to that. So I like to make that distinction here, because we're not saying that the Poynting factor goes away because of any assumption of ideality, right? This is just simply being justified based on doing some back-of-the-envelope calculations for the system we're looking at, and convincing ourselves that in that particular case, the numbers just simply aren't that significant there, and so the Poynting factor might be very close to unity or close to 1, but it doesn't have anything to do with the assumptions associated with ideality. All right. So we've got our assumptions here, and if we go through and do all of these things, we get to a situation where we recover Raoult's law. Right, so simple expression. You've seen this before in other classes, right? And so we have Raoult's law. Again, it's going to be our equilibrium expression. It's our fugacity in the vapor phase for the component I is equal to the fugacity of component I in the liquid phase. And this is what we're going to use for that part of our equilibrium criterion. So now what we're going to do is we're going to think about a binary system. So a binary system is just a system that contains two components, maybe components 1 and 2, components A and B. We'll put names on them at some point, but basically we just have two components in the system. Right, and so if we want to think about describing vapor-liquid equilibrium in this case, we can start out by writing out our governing equations. And because we have two components in the system, we would come in and say we need two equilibrium relationships, one for each of those components. And so we could write out Raoult's law for component 1, for example. And we could also come in and write that out for component 2. All right, and we'll remember that these saturation vapor pressures are functions of temperature, just to remind ourselves of that. So, right, both of these here, these are giving us fugacity in the vapor phase is equal to fugacity in the liquid phase for a given component, under the assumption that components 1 and 2 form ideal gases and ideal solutions. And the Poynting factor is negligible. All right, so that gives us our fugacity-based equilibrium criterion. We're assuming here that the pressure and temperature of the two phases are equal to one another, so those are satisfied. And so we can think about the fact that we have two phases here, a vapor and a liquid, and we have two components. And so we can do a material balance on each one of those phases, and we'd recognize that y1 plus y2 had better equal unity, and x1 plus x2 had better equal unity as well. One of the more simple material balances we can do, but we know that those two material balances have to govern everything because the mole fractions need to sum to unity within a particular phase. Now, if you have a somewhat older version of the Matsoukas textbook, at one point or another there was a typo related to this in the textbook, and so that might be something to take a look out for. But the point here is it's y1 plus y2 is equal to 1. It's not y1 plus x1 is equal to 1. So in any case, we end up with our governing equations here for vapor-liquid equilibrium for a binary ideal system. Right, we have 4 equations. And if we add things up here, we find out that we have 6 unknowns, or 6 variables here, right? So we have y1, y2, x1, x2, and pressure and temperature, right? If we can specify, those are the 6 things that govern this. Now, we need some information about the saturation vapor pressure, but if we know what the temperature is, and we have that information, either the Antoine equation or some other tabulated value of the vapor pressure, then we could figure that out for each of the components. So we have 6 variables, and we have 4 equations. And so this tells us that we need to specify 2 degrees of freedom in order to ultimately solve this system, right? So we need 2 degrees of freedom. And if we specify 2 of these variables, then we can calculate everything else, right? And this is consistent with the Gibbs phase rule, right? So if we think about the Gibbs phase rule, and this is discussed in chapter 10.1, right? But the degrees of freedom in the system are equal to 2 plus the number of components in the system minus the number of phases. And so if we think about this, if we have a binary system, here we have 2 components, and if we have 1 phase, then our degrees of freedom are equal to 3. And if we have 2 components and we have 2 phases, then our degrees of freedom are equal to 2. And that's where we get this balance between our 4 equations and what are ultimately 4 unknowns once we specify those 2 degrees of freedom. So basically here, if we have 2 components in 1 phase, we need to specify 3 things. So maybe a temperature, a pressure, and a composition. But if we have vapor-liquid equilibrium and we have 2 phases and 2 components, then we only need, for example, to specify, say, the temperature and pressure of the system, and everything else is fixed because we fully defined the system. I'll point out too, right, we can do this for other systems. If we have 1 component and 1 phase, we need 2 degrees of freedom, right? Temperature and pressure of a pure component fully defines the system. Or, if we think about something like the triple point, for example, we have a situation where we have no degrees of freedom. There's only a single point where that occurs, and if we have 3 phases in equilibrium for a single component, then that only occurs at 1 point. Right, so we have the Gibbs phase rule that we can use to handle this, because ultimately here we're talking about a binary system, but at some point we're going to talk about systems that contain more than just 2 components. And so it's useful to use this Gibbs phase rule in order to understand how many degrees of freedom you would need to specify to be able to fully satisfy and solve the problem. And so as a result of this situation, again, for a binary system in VLE, under the ideal assumptions here, we have 6 variables and 4 equations, 2 equilibrium equations and 2 material balances. And so if we specify 2 variables, and we are able to calculate the rest of everything and fully describe the system. And so we can break this down into essentially 6 VLE calculations, and these are general. These don't just apply to binary systems. These are basically the 6 vapor-liquid equilibrium calculations that are done. And the simplest case scenario is if we have, a binary system like we're going to talk about here, but we could imagine having these situations become more complicated if we had more components. And so, these calculations, so start off with the bubble point pressure calculation, right? What's going on here is we're looking to calculate the pressure and the composition of the vapor that forms initially in the first little bubbles that start to occur out of a given liquid with composition given as X and temperature T. Now, the brackets that I'm using here on the slide are just meant to indicate that all of the mole fractions in that particular phase are specified. So in the bubble point pressure calculation, we need to know the temperature, and we need to know all of the mole fractions in the liquid phase. And with that information, we can calculate the pressure and the mole fractions of all the components in the vapor phase in that initial bubble that forms as we go into vapor-liquid equilibrium. So the dew point pressure just turns that around. Now we're thinking about that initial condensation that occurs out of a vapor of known temperature and composition, and we'd be calculating pressure and liquid phase composition there. The temperature calculations, both bubble and dew point, do the same thing, except for now, instead of solving for pressure, we're solving for temperature. And we can think about binary flash calculations. We'll see these as we talk about flash processes, where we specify a temperature and a pressure, and that gives us enough to figure out the compositions of everything in the system. So just specifying T and P, for example, in a unit operation, defines what compositions we'll get out of that process. And we could go the opposite direction. We could specify compositions of the liquid and the vapor phase, and then use those to calculate the temperature and pressure that would have to be the situation in order for equilibrium to be occurring. So we're going to see these 6 vapor-liquid equilibrium calculations. They're the same calculations that we do for binary systems, the same calculations we do for ideal systems with an arbitrary number of components, and they're the same 6 calculations that we do for systems with any number of components that have non-ideality involved. And so we want to get real solid on thinking about these 6 calculations that we do to describe vapor-liquid equilibrium and how we ultimately use those to generate diagrams or ultimately solve equilibrium problems using the equilibrium criterion that we've been working to set up.